This video describes how Bohr's atomic model can be applied to electron energy level transitions and Planck's quantum hypothesis. A discharge tube is designed to hold gas at a low pressure. When a high voltage is applied across the discharge tube, the excited gas emits light of only certain wavelengths or frequencies, producing the appearance of different colors. When viewed through a spectrometer or spectroscope, the line spectrum is visible, showing the combination of colors produces the glowing light. This is known as an emission spectrum. This can be shown for several gases. An interesting behavior of matter is that it emits the same kind of radiation that it absorbs. So if white light is shined toward the material, it will absorb those frequencies that it also emits. The absorption spectrum shown represents those colors that are reflected off the material and those that are absorbed. The reflected material is all the colors that are visible. The black lines represent the light that has been absorbed by the atom. It is important to notice that the emitted light is the same as the absorbed light. To understand why this occurs, we need to understand Bohr's model of the atom. Bohr proposed that electrons are confined to energy levels, travel in circular orbits around the nucleus, similar to the planetary model. However, instead of the gravitational force holding the electrons in orbit, it's the electrostatic attraction between the electrons and those protons in the nucleus. Each electron has a certain amount of energy associated with its energy level. As an electron orbits in a given energy level, it does not radiate energy, because the energy remains constant as it orbits in a specific energy level. The lowest energy level, where n equals 1, is defined as the ground state. N is the energy level. An electron in the ground state cannot move any closer to the nucleus, so 1 is the lowest energy level. Any energy level higher than the ground state is known as excited state, where the energy of the second level is higher than the first, the energy of the third level is higher than the second, and so on. Because the energy is greater in each consecutive energy level, they are said to be excited states. Bohr also theorized that these electrons are not fixed in the energy levels. These electrons can undergo quantums from one energy level to another, but they can never exist between energy levels. When an electron jumps from a higher energy level to a lower energy level, the electron loses energy and a photon is emitted with a certain energy and frequency. The energy that the electron loses is the energy that the photon carries by conservation of energy. Because each energy level has a certain amount of energy that corresponds to it, we can define the loss in energy of the electron, which is E initial minus E final. The energy is equal to hf by Planck's quantum hypothesis, which can be further changed to hc over lambda. When a voltage is provided across a gas, the gas glows as a result of the electrons jumping to lower energy levels and giving off photons of certain frequency and color. This is what produces the emission spectrum. It can also be shown that the opposite is true for an electron that jumps from a lower energy level up to a higher energy level. The electron must be absorbing energy from an incident photon, incoming photon, but only those photons with just the right amount of energy will be absorbed. the energy of the photon must be exactly equal to the difference in energy between two energy levels in order to excite an electron. This is what produces the absorption spectrum. If white light strikes an atom, the atom will absorb photons of only those energies that correspond to the energy difference between energy levels in the atom. If we know the difference between any two energy levels, then we can determine what frequencies of light will actually be absorbed when white light is shined on the atom. We can use Planck's quantum hypothesis, which says the energy of the photon is equal to hf, or hc over lambda, and the energy of the photon has to be equal to the difference between any two energy levels. Again, this is what produces the absorption spectrum. Only certain frequencies of light that correspond to the difference between energy levels will be absorbed. It is possible for electrons to move from one energy level to another within an atom, but it is also possible for an electron to be completely removed from an atom. The energy required to completely remove an electron is known as the ionization energy or the binding energy. It is called the ionization energy because the atom is essentially becoming an ion when an electron leaves. In hydrogen, the energy required to move an electron from the ground state to n equals infinity, which is essentially out of the atom, is 13.6 electron volts. As we can see in the diagram, the ground state has a level of negative 13.6 electron volts, which is the lowest possible energy level. The highest possible energy level is 0 electron volts. The electron must gain 13.6 electron volts to move from the ground state to a point which is outside of the atom. Using the equation to determine the energy of the photon, E initial minus E final, we get negative 13.6 electrons. The energy required is 13.6 electron volts. The negative sign indicates that the photon is actually being absorbed to get the electron to move from a lower energy level to a higher energy level. If the energy difference is positive, this means the photon is actually emitted and not absorbed. It is important to understand the variety of energy level transitions that can take place in any given atom. There are three major series that indicate the type of energy level transitions that may take place within a hydrogen atom. The first series, known as the Lyman series, describes all transitions that take place where an electron moves from a higher energy level to the ground state, where n equals 1. The second series, which is known as the Balmer series, describes all transitions in which an electron moves from a higher energy level to the n equals 2 level, or the second energy level. And finally, the Paschen series, which describes those transitions that take place from any higher energy levels to the n equals 3. Now that we've learned some of the fundamental principles of Bohr model and energy level transitions for electrons in atoms, let's try a few practice problems. Determine the wavelength of the first line, which is the transition from the second energy level, n equals 2, to the ground state, n equals 1, for hydrogen. And also, determine which region of the electromagnetic spectrum this type of wave is. Pause the video for time to work on the solution. To determine the wavelength of the first Lyman line, we first have to determine the difference in energies between the given energy levels, and that is E initial minus E final. And that can be set equal to hf, or hc over lambda. The initial energy level is negative 3.4 electron volts. The final energy level is negative 13.6 electron volts. Taking the Determine the wavelength of light emitted when a hydrogen atom makes a Balmer line transition from the n equals 6 level to the n equals 2 level. Pause the video for time to work on the solution. To determine the wavelength of the light, we can use Planck's quantum hypothesis. We first have to determine the energy difference between the initial and final levels. E initial is negative 0.38 electron volts, and E final is negative 3.4 electron volts. We find the difference to be 3.02 electron volts. But when we plug in the energy level difference to the Planck's quantum hypothesis equation, we have to have the energy in joules. So we need to convert the 3.02 electron volts into joules by multiplying by 1.6 times 10 to the minus 19. We find the energy difference in joules to be 4.832 times 10 to the minus 19. We then plug that energy level difference into Planck's quantum hypothesis formula. We can plug in Planck's constant and the speed of light c, and then solving for the wavelength, we find the wavelength to be 4.6 times 10 to the minus 7 meters. Now let's look at a problem taken from a past AP exam. Pause the video for The first question asks us to draw arrows indicating the possible transitions that could take place for an electron going from n equals 3 to n equals 1. The first transition is from n equals 3 to n equals 2. The second transition could be for an electron at n equals 3 jumping all the way down to the ground state where n equals 1. And the third possible transition is from n equals 2 down to n equals 1, the ground state. This transition would only take place if its first transition was from n equals 3 to n equals 2. Then to get all the way down to the ground state, it would have to undergo another energy level transition from n equals 2 to n equals 1. Part B asks us to determine the longest wavelength possible. The longest wavelength results from the smallest frequency and therefore the smallest energy. The smallest energy takes place from n equals 3 to n equals 2. To determine the energy of a photon, we have to use the energy difference between n equals 3 and n equals 2. The initial energy is negative 0.75 electron volts. The final energy is negative 12 electron volts. And taking the difference of the two, we find it to be 11.25 electron volts. This is the energy of the photon. But in order to figure out the wavelength, we have to use the energy in joules. So we have to convert 11.25 electron volts to joules by multiplying by 1.6 times 10 to the minus 19. And we find the energy of the photon in joules to be 1.8 times 10 to the minus 18. We can plug this energy into Planck's quantum hypothesis formula, E equals hc over lambda. We can also plug in h, Planck's constant, c, the speed of light, and solve for lambda, or the wavelength. We find the wavelength to be 1.105 times 10 to the minus 7 meters, which is 110.5 nanometers. That is the longest possible wavelength. C asks us to determine the ionization energy, which is the energy required to kick an electron completely out of the atom, where the energy level is equal to infinity. If the initial state is the ground state, where the energy equals negative 12 electron volts, and where n equals infinity, the energy equals 0, then the ionization energy, or the energy required, is 12 electron volts. Converting that into joules, we multiply it by 1.6 times 10 to the minus 19, and we find the ionization energy in joules to be 1.92 times 10 to the minus 18. Part D asks us, what effect would an incident photon with an energy of 11 electron volts be on an electron in the ground state? If the energy of the incident photon is 11 electron volts, then there's no energy level difference that corresponds precisely with 11 electron volts. So the photon will not be absorbed and the electron will remain in the ground state. Remember, for a photon to actually be absorbed, it has to have an energy exactly equal to an energy level difference. Finally, part E asks us, what effect would an incident photon with an energy of 14 electron volts have on an electron in the ground state? Well, the ionization energy is 12 electron volts. That's the energy required, at least, to get the electron from the ground state entirely out of the atom, where n equals infinity. But if the photon energy is 14 electron volts, larger than the ionization energy, it will still be absorbed, and the electron will be completely removed from the atom. And because the energy is larger than the ionization energy, then the electron may also have some leftover kinetic energy. Thus, ionization does take place. So, notice, for an electron to move between energy levels, it has to absorb a photon with exactly the right amount of energy that corresponds to an energy level difference. However, if the energy of the photon is greater than the ionization energy, then the electron can still absorb that photon, because not only is it kicking it out of the atom, but it is also going to give it some extra kinetic energy.